welcome to another episode of Coast Connections. It's my pleasure this evening to have with us the National Research Council of Canada from the Herzberg Institute of Astrophysics and Astronomy here in Victoria, right here on Vancouver Island. And joining us tonight is Luc Simard, who is the Director of Astronomy Technology. How did I do?
Very well. It was awesome. Glad to be here.
Very, very good. Not the shortest title in the world, but
I apologize for that.
No problem at all. It's a fiercely interesting title. And Luc, you're here to take us to infinity and beyond.
That's the plan, so I hope it's a good ride.
I hope so too. The Herzberg Institute is really the gateway to the universe for Canada.
That's correct.
And we're going to talk tonight about the optical telescopes and the radio telescopes and the different images that we see with both of those. And we're going to help our viewers and myself bring this out of this world technology into our hands, how that data is actually used and the research is used in our day-to-day lives. Well, so let's break it down and bring it down.
Great.
So the first thing we want to talk about is how first the Plaskett telescope. We have an image of the Plaskett telescope from Victoria, and that's an optical telescope.
That's correct. Yeah. So it's it's 100 years old, and it's one of the local telescopes that we have on Canadian soil, and we have bigger ones elsewhere in the world. But the Plaskett is our own, and we get to use it every night where we have clear skies. And the optical telescopes are mirror-based, so they use big mirrors like the ones that we use every day, but they have a special shape, and the shape of these mirrors collect the lights from the sky and focuses it onto very nice images for us to look at and make measurements.
And we have a couple of images of what an optical telescope actually sees, and we'll bring those up as well, just to show our viewers, because we're going to show the difference between what a radio telescope can see and what an optical telescope.
Yes, so our optical images look differently than the radio images. And when we talk about optical and radio, we're really talking about light. And the only difference between radio waves and optical waves is the wavelength. So radio waves are much longer and the optical waves are much shorter. And to give you an idea, radio wave is about 20 centimeters long, and an optical wave is 1/1,000,000th of a meter. So it's about 100 times narrower than a human hair. And that's the only difference between the two lights. And different wavelength means you need different kinds of telescopes. So optical telescopes and radio telescopes, they do the same thing with different kinds of light.
Okay. And the image that we're seeing now, Luc, that's taken with a optical?
That's taken with an optical telescope. This one is an image from the Canada, France, Owyhee telescope. It's a telescope the mirror is 4 meters in diameter, so it can look really far in the distance. And it's taken with one of the biggest digital cameras in the world. It's a 340 megapixel camera.
Wow.
We put it on the telescope in 2002. And since then, we've been imaging the sky with images like this. So what you see on there is a spiral galaxy that looks like our Milky Way galaxy. So if you could warp out of the Milky Way and then on a spaceship, you would see the Milky Way pretty much like a galaxy like this one.
Wow. So. And that image was taken from the Canada-France telescope, which is on top of Mount Mauna Kea.
On the Big Island of Hawaii, which is a great place to do astronomy. So the Canada-France Owyhee telescope was put in operation in the late 70s. And since then, it's been taking these amazing pictures of the sky.
And there'd be very little light pollution there on top of Mount Mauna Kea.
That's right. Yeah. So light pollution is the enemy, the same way that radio pollution is the enemy of radio telescopes. So we need to get away from bright lights that can ruin the images for us. And so in Victoria, it's getting to be a bit of a problem because the city is growing and the telescopes are not that far from downtown. And so
100 years ago when they put it in, there was no light pollution.
There was nothing.
Nothing to consider.
And even I started as a grad student at the University of Victoria in the 1990s, 1990 to be precise. And even then the city was smaller. And over the years, you could watch it grow and become brighter, even though we have some bylaws that keep the light pollution down. And that's a great help for us. And
now let's talk a little bit about a radio telescope. And I think we have an image of one that we're going to bring up here in a second. A graphic, actually, that talks about how a radio telescope actually works. Break it down for us, Luc.
All right, so we start from the dish itself, and it's a satellite dish like any satellite dish that people use for satellite TV, direct TV or whatever. It's a dish that collects the radio waves from the sky, and then it sends it down to a receiver where it's amplified. We're talking about very, very faint signal. So if you take all the energy collected by all the radio telescopes in the world since the beginning of radio astronomy in the 50s, the total amount of energy, radio energy, is the same as a snowflakes hitting the ground. That's how little energy we're collecting from the sky, but our telescopes are so sensitive and precise that we're able to build images of the sky with that little energy.
That finite amount of energy.
That's right.
Yeah.
With that, a very small amount of
Snowflake
energy,
size.
we can create all these images that you've seen of the radio sky. And so it goes from the receiver, it gets amplified, and then it goes to a digitizer, which takes all the signals and turns them into zeros and ones. And the 0 and 1s are then sent to something called a correlator, which is the brain of the radio telescope. And the correlator takes the 0s and 1s and turns them into pictures, radio images of the sky. And I think we've got some of those images with us.
Yeah, let's show the two radio images.
Yeah, they look like, they're going to look like a picture on the screen. That's right. But those are images that you cannot see with your own eyes. You can only see them in radio waves. And what you see up there is a region of our Milky Way galaxy, and you see a region filled with gas and dust, and what looks like those bubbles are actually stars that exploded and blew away the material to create an empty void around them, and that's what you see there. So stars are born, they live, they die, and what you see on those pictures are some of those dead stars, as well as, in this case, what we have here is a star-forming region. So baby stars being born for the first time. We see these nurseries across the entire Milky Way galaxy, and we map them out with our radio telescopes and create those beautiful pictures that you see.
That is phenomenal. The difference between the image that you can get from a radio telescope compared to an optical one is phenomenal.
It's quite amazing, and in fact, what's a bit bizarre is that stars don't produce a lot of radio waves. So if you want to see stars, you look in the optical, and if you want to see the interstellar gas, you look in the radio. So depending on which type of telescope you use, you look at different corners of the universe, and that's very important. So as we try to understand the universe, we need all these telescopes, not only optical and radio, we need X-ray telescopes, which we have, gamma ray telescopes, which we also have, and then we put together a picture of the universe using all these different eyes. So it's like building new eyeballs that we need.
It's tremendous, tremendous technology. Now, you've got some amazing props that you've brought with us that brings, again, the out-of-this-world information right into our hands. So, Luc, let's start with the interesting-looking circuit board that you have here.
So this board is what we call a digitizer, and that's what takes the signals from a radio telescope and turns them into zeros and ones. It turns the signal into a digital signal, and that's what's fed to the correlator to produce the image. And
so the radio wave that the telescope receives is turned into a 0 or 1.
That's right. A series of 0 and 1s, lots and lots of them.
Through a processor like that.
That's right.
The 0s and 1s are then, or a correlator, the 0s and 1s are then turned into
images by the correlator. So, the way I look at it is you've got a radio telescope, which is your eyeball.
Right.
And then you have a bunch of cables, which are the optic nerves. And then the digitizer takes the signals along the nerves and translate them into a signal that can be understood by the brain. And then the brain, which is the correlator, is then produces the images. So the digitizer is this board here, and then the brain of the radio telescope is something that every gamer will recognize. It's a graphics card. And as it turns out, the graphics cards can be used to do exactly the type of operation that a radio telescope brain needs to do to produce images from the radio signals. And so instead of having a single graphics card like this one, we have hundreds of them working together as a brain to produce images from our radio telescope. But this is off-the-shelf graphics card and we just grab them and program them to do what we need for our radio telescopes.
So we're using the technology in the reverse way as well. We're using those to power and feed the radio telescopes, but the information we're getting from the telescopes, we're adapting for things like our cell phones.
That's right. So everybody carries a radio receiver with them. Your cell phone is a radio receiver. It's able to tune to very powerful signals that we generate with our towers and our satellites, but fundamentally it's a radio receiver. It listens to a different window of the spectrum. So you hear sometimes that companies were bidding for sections of the spectrum. They're bidding for ranges of frequencies that they can use to broadcast their signal. So what a cell phone does is they listen to a very specific range of frequencies that we broadcast on, and the radio telescopes use other windows to listen to the universe. And so they don't interfere with them, hopefully, but sometimes they do. And that's how we get to divide the spectrum in different regions, some for cell phones, some for satellite radio, and some of them for radio astronomy.
Very cool.
So we try to, with all the cell phones and satellite TV, we're increasing the radio light pollution of the planet, so that makes the radio waves from the sky harder to detect. And so we need to really say, this is your window, that's my window, let's work together to make our observation at the same time that I can make a phone call.
Just break that down a little further for me, Luc. The radio pollution, what is that? Is that noise?
It's anything that produces radio waves that you don't want. So for example, we have a radio observatory in Penticton, and you're not allowed to take your cell phone on the site. You have to turn it off because the cell phone would completely blind our radio telescope. So the cell phone is also a radio source, and the power of a cell phone is enough to completely blind these massive radio telescopes that you would see on our site.
They're that sensitive.
They're that sensitive.
Wow.
Yeah. It's so that's why when we have visitors, we say, please turn off your cell phone so that we can continue to observe the sky. The sky is a lot fainter than any human-made signal that we produce today, and with more internet and more satellite, then the sky gets obscured. The radio sky gets obscured by the man-made activity.
How do we protect it? How do we protect the radio sky then?
So sometimes what we do, what we try to do is limit the sources of radio interference near the radio telescope. But what we try to do is divide the spectrum, the electromagnetic spectrum, into ranges, windows that we can dedicate to a cell phone or a satellite or a radio telescope. So if I'm listening to this window, I can't see what's in the other windows. And so that's how we play nice together. And that's why it's also very much regulated by governments. So companies can only use these frequencies and nothing else, because if you get out of bounds, so to speak, you ruin somebody else's work or enjoyment of those frequencies.
Amazing, amazing. Now the same processor that's in the cell phone is also in the board.
That's right. So
for the radio telescope.
What you really have on the table is three kinds of technology. So we have a CPU, which you find in lots of computers. The CPUs are great because they can handle all kinds of tasks. You can use them to browse the net. You can use them to do word processing or make a presentation or something. So CPUs are great that way. Then we have a GPU, like a graphics card. And these things, what they do is they are very, very powerful at very simple things. So when you look at a video game, it's basically a bunch of triangles drawn on the screen. And the GPUs are good at drawing triangles on the screen, triangles of different sizes, but that's all they do. And they can't do a whole wide range of different things, but they do it really fast. So what we do is we take GPUs and we train them to do one thing only, and they do it really, really fast. So that's a graphics processing unit. And then this gizmo here, we have a CPU like any computer, and then this other chip that is hiding under the heatsink is called an FPGA. So it's a field programmable gate array. And it's like a CPU, but I can change its personality. So imagine a CPU having one personality, or a GPU one personality. And in this case, I can take this chip and say, you're going to be dividing numbers. And that's all you're doing.
Yep.
And it does that really quickly and really efficiently. Then I can tell it, no, what you're going to do is subtract numbers. And you load up a different personality and you reprogram the chip to do something else. And the advantage of this chip is that it's very power efficient. And that's very important. So, for example, the big companies today like Microsoft and Amazon are running these massive data center with tens of thousands of computers in them. So that requires a lot of electricity. So the main cost of these data center is electricity and cooling. Things get hot and you want to keep it cool. With an FPGA, if you consume less power for the same amount of calculation, then you get ahead in your power budget. So you save money on electricity, and that's a big thing.
Wow. And that's all coming from astrophysics.
Well, so that's
correlates.
So, for example, we're working on a new radio telescope called the Square Kilometer Array. We're building the brain of that radio telescope. That telescope will generate every second as much data as the global current internet is doing. So imagine all the internet traffic in the world today, condense that in 1 second. That's how much data this radio telescope will generate, and we're building a brain to handle that data in the not so distant future. It's the equivalent power of, I think it's 100 million PCs is what we're talking about, and this brain is being designed and in Penticton, right here in our backyard.
The Square Kilometer.
The brain for the Square Kilometer Array telescope, which will be the most powerful radio telescope in the world, the brain of it is being designed in British Columbia.
Wow.
We have the A team for that kind of work.
That's
and
tremendous.
It's using chips like this one.
Now that SKA, that telescope, that's going to be, is that in Western Australia or?
So there's a part of it in Western Australia and another part in South Africa. And so
They're
there's...
going to be talking to each other?
They won't be talking to each other. It's one of them listens to one type of frequencies, and the other one listens to another type of frequency. So they observe separately, and they can observe the same object, but they're different frequencies, and that's important because again, if you use different frequencies, you see different things, and that's important to understand the science of the universe.
And they're applied to different things as well.
That's right.
The frequencies.
The frequencies are applying to different things. To give you an idea of the power of this radio telescope, it could detect an airport radar at a distance of a few tens of light years. So imagine there's an airport radar out there around another star. I'm not saying there is, but let's say there was, knock on wood, we would be able to detect it. So, imagine your local airport radar, stick it out there light years away, and we would be able to detect it with our radio telescope.
And that's with today's technology.
With today's technologies, with a tiny bit of boost. But to go back to your question about, astronomy in real life, these FPGAs are powering our online shopping. They're powering the big databases that run our healthcare system or the stock market. And the companies like astronomy because we're dealing with lots and lots of data, but data is public, and as opposed to being confidential. So because the data is public, their programmers can look at the data and then play around with their system to optimize the speed and make them faster and better and all that good stuff. So that's how astronomy enters the real world in that sense.
And you mentioned earlier radio astronomy was only discovered in was it 1932 or something?
That's right. So in the 1930s we had the first people playing around with the first, basically they were developing phone systems and they were looking at radio antenna and then realized that there were these these sources of radio waves that they didn't know where it came from until they realized they came from the sky, and that was the birth of radio astronomy.
And I think that was the Milky Way at the time.
Yes, the Milky Way is a powerful radio source. Jupiter is another one. There's dead stars that are also powerful sources. And the beauty of it is you can literally build your own radio telescope in your backyard if you want. I did that in high school. I built a radio telescope in my backyard and listened to the radio waves from the Milky Way, which was
That's
great.
Yeah, that's very cool. Let's talk a little bit about the CHIME telescope that's in Penticton. Again, that's another amazing state-of-the-art telescope. And talk to us about, it opened, I think, just in September, a month or two ago.
That's right. We had first light at the beginning of September, September 7th. We had the Minister of Science there on site to put the last piece onto the telescope so we could turn it on. And CHIME is amazing because it's going to try to measure the expansion of the universe in a new way. So it's going to make a huge map of the sky, and then from that map, we're going to look at the structure of the expansion of the universe in that map.
Because CHIME stands for, I think it's the Canadian Hydrogen Intensity Mapping Experiment. Yeah.
It's a beautiful acronym. And if you're going to do something in astronomy or anything, choose your acronym carefully, because you got to have a cool acronym. I mean, CHIME is beautiful.
That's very cool.
It's very cool, and it says exactly what it does. And it's a bizarre looking telescope because it looks like a bunch of cylinders. The antenna don't look like a dish like people are used to. They're just cylinders, and the cylinders produce a thin window on the sky. The telescope does not move, but the sky moves around. As the Earth rotates, the stars and the universe fly by the beam of the telescope, and then we record what the telescope sees with time, and then we can build up an image from different slices in time. And it's a Canadian-made telescope. It's a collaboration between McGill, University of Toronto, and UBC. So Canadian-made, university professors, grad students, postdocs, that's their baby. And it took them years to put it together. They kept the cost down, make it cheap by using cell phone technology, designing boards with these that you see here, using graphics cards. Everything was meant to keep things cheap, but extremely powerful. And that's mission accomplished. It's going to be beautiful. It's going to take data over the next 5 years, and in 5 years we'll have a new measure of the expansion of the universe, and that's going to be something beautiful.
So some of the data that CHIME will be collecting, Luc, how will we find that in our hands?
I think the beauty of today's science is that everything is on the internet. So people are able to go online and, I don't know, look up the latest pictures from a robot flying around Saturn or the sunset on Mars. The same thing goes with these new survey telescopes. We put everything online, and so once the scientists have built pictures out of the data, they will make them available online to other researchers, but also the public will get a chance to see what the CHIME map of the universe looks like. And those things are just amazing. They become almost artwork in their beauty. And that's something that I really enjoy, is you never know what the picture is going to look like, and when it does, it's just wow, we're looking at this for the very first time, and everybody gets to share in the adventure because of the power of the internet. You can click, here's the map. And I think that when I talk to kids about science, I tell them you live in a privileged time where you can do this. As kids, you can just get on the internet and see all this wonderful data for yourself and see the views of the universe that these new eyes bring to us. I'm jealous because that's not how I grew up.
But now you're involved totally in the field yourself.
That's right.
Yeah, yes. Seeing these new surprises every day must just be so inspirational for you and your team there at the Herzberg Institute. And
sharing it with people is also something that we love to do, because we're all discovering the universe together, and it's a great privilege of our job to be able to do that with people, and we do it every chance we get. And the interest that we get from people is absolutely tremendous, and it's always fantastic to talk to people, and the questions they come up with are very profound. I give talks to all kinds of audiences, and I would say that the scariest audience is actually the grade school kids, because they're not afraid of asking questions because they think it's going to be dumb. No, they go for it, and they ask you these questions. You go, okay, all right, what's outside the universe? Oh, that's a good question. I don't have a good answer to that.
Okay, here's a good question. With all the observations you've done with optical and radio telescopes, Luc, have you ever seen a UFO?
No. No, I haven't seen. Unfortunately, I haven't seen like an alien artifact
Yeah.
or anything like that. And the sky is surprising because people think that the sky does not change, but there's lots of things that change in the sky. We have satellites flying overhead. We have Venus, which can be really bright. Even Jupiter, Mars, they're bright objects. And sometimes you see something in the sky and you think, well, that can't be natural because it changed so fast. But it does sometimes. Sometimes it's a glint of sunlight off the solar panel of an orbiting satellite can create a big flash, which can take you by surprise. But I'm sad to say that no, we haven't. I have not seen anything alien, or we haven't detected any radio signals of a artificial nature. But who knows, in the future that might come, because the other thing I like to say is our optical telescopes will be powerful enough to detect life on another planet around another star, like the biosignatures of life. Is there a forest? Is there oxygen? We'll be able to see that with the new telescopes that we're working on. And that's going to happen in, I would say, the next 15 years. We'll have an answer to that question. Is there a forest around another star?
Yeah.
And our telescopes will be able to do that.
Tremendous. Luc, I wish I could expand time because we've just run out of time here with our interview. We just got started on this tremendous topic, and you're just a fount of knowledge, and it's been really fun to have you here.
It was a real pleasure to be with
Yes.
you tonight and with all the people watching.
Thank
you very much.
And people can also go to the Herzberg Institute there in Victoria. It's open to the public for stargazing parties and things like that.
It's open in the summer.
In the
So we
summer
have
for
these
that.
summer nights. So every weekend we host star parties, and they're very popular. People come and look through the big telescopes and the small ones also. And it's very popular, and it's a beautiful experience.
Very nice.
Yeah, so if people are in the neighborhood, please drop by.
Lovely. Drop by and look up. So thanks for joining us for this edition of Coast Connections. We've been talking with Luc Simard from the Herzberg Institute of Astrophysics and Astronomy in Victoria. Thanks for watching. We'll see you again next time.